in this lecture, I am going to talk a little bit more about first order differential ODEs. I am going to talk about a system of first order ODEs. Then I will talk about a linear system of first order ODEs. Now, a system of first order ODEs is something that you have all encountered in chemical kinetics courses. So, that is you see it very often, and what I will try to do today is to just give you some basics about what a system of ODEs looks like and what are the techniques that you can use to solve it. Okay. For the particular case, when you have a linear system of ODEs, if your system of ODEs is not linear, then of course, you have to use other techniques to solve it, but at least in today's lecture we will focus on solving a linear system of first order ODEs. So, first let me tell you what I mean by a system of first order ODEs. So, we saw in the last time that we wrote something like dy by dx is equal to f of x y, and we said that this is a first order ODE, this is one first order ODE. Okay. On the other hand, you can have something like this. So, dx1 by dt is equal to f of x1 x2 or f1 of x1 x2 up to xn and t, and you could have dx2 by dt is equal to f2 of x1 x2 up to xn and t, dx3 by dt is equal to f3 of x1 x2 up to xn and t, so on. I will just put a few dots. dxn by dt is equal to fn of x1 x2 up to xn and t. So, now here I have one independent variable, that is t. So, one independent variable t and n dependent variables x1 x2 up to xn. Okay. So, this what I wrote here is a system of n first order ODEs. It is not one first order ODE, but it is a system of n first order ODEs, and so this is what we mean by a system of differential equations. Okay. Now, let me take one example. Okay. So, suppose you have let us say you have dx by dt is equal to 2xy plus cos t, and you have dy by dt is equal to 3y square sin t. So, this is a system of two first order. So, this is an example. This is a system of two first order ODEs. Now, see it is possible to convert second order ODE. So, one second order ODE into, so let me emphasize one second order ODE into a system of two first order ODEs. So, I will just show you how to do this. Suppose I have d square x by dt square is equal to f of x y or f of x t. Okay, so this is a second order ODE. Now, I can write this dx by dt is equal to y and dy by dt is equal to f of x t. This is a system of two first order ODEs. So, a single second order differential equation has been converted to a system of two first order differential equations. Okay. So, the first differential equation is dx by dt equal to y, the second differential equation is dy by dt equal to f of x t. Now, this is a very useful thing to do. Okay. In particular, let us consider, so if we have an nth order ODE, we can convert it into n first order ODEs. Okay. This is just a natural extension of what we did in the previous problem. So, if you had an nth order ODE, then you can convert it to n first order ODEs. So, a general linear ODE, okay, a general linear ODE is written as dn, I will just take x and t, x by dt raised to n, okay, plus some constant, I will just C1 dn minus 1 x by dt raised to n minus 1 plus C2 dn minus 2 x by dt raised to n minus 2 plus so on up to you have all the way to c, you can take, you go to let us say c n minus 1 d by dx d by dt of x plus c n x equal to 0. So, x is the dependent variable, x is a function of t. Okay. So, you have a constant term. So, or you have x, you have a term that depends on x, okay. Then you have a term that depends on dx by dt, then you have a term that depends on d square x by dt square and all the way up to dn x by dt raised to n. So, this is a linear ODE and equal to 0. So, it is homogeneous. Okay. So, since the right hand side was 0, there is no constant. Okay. So, each term has a derivative to 1 power, okay, and it has nothing else, it just has a constant. Now, such an equation, okay, this linear ODE, okay, you can write the solution. Okay. So, linear ODE and linear ODE, let me emphasize. So, it is C1, C2 up to Cn are constants. Okay. So, what you have is linear homogeneous nth order ODE with constant coefficients. What you can do is you can use the method that we did earlier. We can convert it to n first order ODEs with, and what will happen is all of them will have constant coefficients. You can easily do this. So, I can write let me call x as x1, then dx1 by dt equal to x2, dx2 by dt equal to x3, dx3 by dt equal to x 4, and you will get d x first derivative, second derivative, third derivative. So when you go to the last one, then you will get d x n by dt. Okay. This will be minus c 1 times now you will get x n minus 1 and so on, c 2 times x n minus 2 and so on up to c n times x 1. Okay, that was the original differential equation. So what I did was I replaced each of these by one of these x 2, x 3, x 4. Okay. So finally, what I got is each of these is a linear first order differential equation with constant coefficients. Okay. And finally, you get this equation. Okay. Now, so now I can write this. Okay. So now let us consider a more general case. So independent variables variable is t, and dependent variables x 1, x 2 up to x n. Now, system of ODEs so d x 1 by dt. Okay. And now, what I will write is d x 1 by dt, I can in general it will be a 1 1 x 1 plus a 1 2 x 2 plus a 1 3 x 3 plus all the way up to a 1 n x n. Okay, these are the constants. I am just calling the constants a 1 1, a 1 2, a 1 3 and all the way up to a 1 n. Similarly, I will have d x 2 by dt, and here I will have a 2 1 x 1 plus a 2 2 x 2 plus a 2 3 x 3 plus all the way up to a 2 n x n, and you can go all the way to d x n by dt is equal to a n 1 x 1 plus a n 2 x 2 plus a n 3 x 3 plus all the way up to a n n x n. Okay. So, I wrote it in this form, okay, and this actually, when you have a system of ODEs with constant coefficients. So, with constant coefficients, notice that none of the terms contains only the independent variable. Each term contains one of the dependent variables, okay, to 1 power. So it contains one of the dependent variables to 1 power. So this is a system of ODEs with constant coefficients, okay, and now I can use matrix methods, matrix notation first. Okay. So, how do we use matrix notation? So, what we will do is we will say that let me say x vector is equal to, okay, what I will call this as this will be a column vector x 1 x 2 all the way up to x n, and I will write a matrix as a 1 1, a 1 2 up to a 1 n, a 2 1, a 2 2, a 2 n a n 1, a n 2, a n n. So, with this notation I can write this differential equation in matrix notation as dx vector by dt is equal to a times x vector. A is a matrix, x is a vector, and I can write in this very simplified notation. Okay. So, this system of linear ODEs can be written in matrix notation. Actually there are a lot of nice things you can do with this notation. Okay. It is not we can actually use the matrix to solve for this. Okay. Now, suppose I had an equation dx by dt is equal to a times x, where this is a scalar equation. Okay. Now, a is a constant, okay, then you will write solution x is equal to a e raised to a t, okay, plus b. So, a and b are constants, or rather you won't write that way, you will just write x is equal to a e raised to a t. Okay. A is an arbitrary constant. Okay. So, if you just had a scalar equation dx by dt equal to a x, the solution would be x equal to a is a constant times e raised to a t. Okay. Now, this what you have here, okay, this is a matrix version of this differential equation. Okay. So, this is a matrix version of this differential equation, okay. And so you should be able to use very similar methods to solve for it. Okay. So now we can ask the question, so what can you do to solve this? Okay. So, remember our goal is to solve for x, okay. In this case you are supposed to solve for the vector x, okay. So, goal is to solve for the vector x, okay. So, what we will do, I'll emphasize this point. So, goal is to solve for x vector, okay. That is all those variables x 1, x 2, x all. So, these n variables we are supposed to solve for them. Okay. So, what is the vector that will satisfy this differential equation? Okay. Now, here this is where we use some of the matrix methods that we learned. Okay. So, now suppose I had a times x lambda equal to lambda times x lambda. Okay. So, this is my eigenvalue equation, eigenvector equation. Okay. So, these are this is an eigenvalue and eigenvector of A. Okay. So, x lambda is the eigenvector and lambda is the corresponding eigenvalue. So, now suppose I take this, suppose I knew some x lambda which satisfied this, then what I can immediately write is that d by dt of x lambda is equal to lambda times x lambda, okay. And what I can see this is that if I had so d by dt of x lambda equal to lambda times x lambda is actually a system of equations, that is if x lambda was written as x 1 lambda, x 2 lambda up to x n lambda. Then this differential equation is actually a set of n differential equation d x 1 lambda by dt is equal to lambda x 1 lambda and so on, okay, up to d x n lambda by dt equal to lambda times x n lambda, and each of these has a solution x 1 lambda equal to e raised to lambda t times some constant, I will just call it C 1 all the way up to x n lambda equal to C n e raised to lambda t. Okay, so, all these c's are arbitrary constants. Okay. So, this, so we immediately see that e raised to lambda t is a solution. Okay, e raised to lambda t multiplied by some constant. So, then what you can do is you can we need x lambda to satisfy a x lambda equal to lambda times x lambda. Okay. So, if a x lambda equal to lambda times x lambda, okay, then we can clearly see that this e raised to lambda t, okay, plays a role in the solution. Okay. So, then e raised to lambda t, okay, plays a role in solution. Okay. So, then I can write my solution as I can write x lambda e raised to lambda t. So, if I write x lambda times e raised to lambda t, okay, so if I write if I take d by dt of this whole quantity, okay, so x lambda is clearly a constant. Okay. So, this is just x lambda times, now e raised to lambda t, if I take the differential of that I will just get lambda e raised to lambda t. Okay. Now, if I take the lambda outside I can write this as lambda times x lambda, well, okay, I will write it lambda times x lambda e raised to lambda t. Now, lambda times x lambda is just a times x lambda e raised to lambda t. Okay. So, clearly this is a solution of system of ODEs. Okay. So, what we did was that by using this eigenvectors and eigenvalues, okay, we can write the solution of ODE. So, x lambda e raised to lambda t is a solution of dx by dt equal to a x, where x lambda is an eigenvector and lambda is the corresponding eigenvalue. Okay. Now, in general there are n eigenvalues and corresponding eigenvectors, and each of them can give a solution. Okay. So, so what we have seen is that what we have seen by this is that we have what I want to emphasize is that system of linear homogeneous first order ODEs can be solved using eigenvalues and eigenvectors. Okay. So this is a very important message that I want to give from this lecture, that if you have a system of linear homogeneous first order ordinary differential equations, then you can solve this system of ODEs using the method of matrices. Okay. So, there is a very important connection that we are making between matrices and linear ODEs. Okay. So, in the next class, next lecture, we will try to see how to write the general solution and particular solution of this system of linear ODEs, and we will talk in general about homogeneous ODEs and their solution. Thank you.